Okay, moving on. What about the node of Ranvier? So again, these are things that we wish we knew of before so that we understand what we encounter in neurology in the upper years. So this is an electron microscope picture of the node of Ranvier. So those nodes of Ranvier means they're naked, meaning there's no myelin sheath there. It means something must transpire here to make conduction of nerve impulses faster. What makes it faster? There has to be something here that adds to that electrical impulses. So I use a very familiar figure to help explain this quite difficult topic. So this is a neuron over here. That's the soma, and this is its axon. So its axon is enveloped by myelin, by the Schwann cell or the oligodendrocyte, depending on where you are. So it leaves these myelinating cells intentionally leave gaps here. And for it to be naked, it means there must be something there that is that increases the conductivity of electricity in that area. Yes, not just because of the lack of insulation, but there must be something there actively adding fuel to the fire that is being that is jumping here in the axon. Okay, enter the Schwann cell, okay, or the oligodendrocyte for that matter. So the Schwann cell has its villi over here. So it has extensions of itself. It wraps around in layers around the axon here. So that's your Schwann cell. And these make contact with your axon. Next. So in med school, we stop here. No? Okay, ito ang node of Ranvier. That's it, period. Next. But now we're telling you there's more to it than that. So this is the node of Ranvier. This is what we call the paranode, where those villi of the Schwann cell will connect with the axon. So that's called the paranode. And extending beyond, so with no contact with the outside, the extracellular fluid here, no contact with, because of this form, disconnections with the Schwann cell, make sure that the electrolytes here are locked in inside here. So nothing mixes with the electrolytes here. So node of Ranvier, paranode of Ranvier, juxtaparanode of Ranvier. One is exposed, one is locked in, and one is inside. So this is your node of Ranvier, and this is your astrocyte, meaning the astrocytes are there to intentionally facilitate the transmission of electricity here at the node of Ranvier. So this is the biochemical way of looking at it. So Schwann cell extensions locking in the insides of that internal environment here. So you have proteins from the Schwann cell, you have proteins from the axon. So essentially closing the door to the outside world here. And you have these sodium channels here, which are the ones that help facilitate the transmission of electricity. And you have channels here as well, and we will get to that in a while. So as you will encounter, in some patients, the myelin sheath of the axons will be destroyed. And most of the time, this will be destroyed by antibodies the body forms against itself. So things that should not happen, but it happens. So antibodies against your very own proteins can destroy your myelin sheath as well as the axons inside. So what happens here? Using SpongeBob as our guide. So we have neurofascin 186 or NF186 for short. What is NF186? So again, I'm just introducing you certain proteins that are newly discovered and help us understand what's going on in the future. You will need to come back to this lecture again to get it. Okay, what is neurofascin 186? So as you can see, it is a part of, it's a protein coming from the node of Ranvier itself. So it's there to maintain the blood-brain barrier. It keeps the blood-brain, it's there to maintain the node of Ranvier intact. So anything happens here, neurofascin 186 is there to repair it, keep it normal. Okay, and that's the biochemical way of looking at it. That's NF186 here in yellow. So it is a protein from the axon, which is extending outward towards a protein from the Schwann cell. Next, neurofascin 155 or NF155. As you can see here, it comes from the Schwann cell. So it comes from the Schwann cell and it interacts with the juxtaparanode part over here. So they do not interact and they should not interact. So that's NF155 coming out from the Schwann cell over here, touching on a protein coming out from the axon. So those proteins coming from the axon this time are contactin 1 and the Casper1, the contactin associated protein 1. So they are from the axon's juxtaparanode and they interact with the neurofascin 155. They annoy it. Okay, so here is the biochemical picture of it. And lastly, you have gliomidin. So gliomidin is a protein expressed by that part of the Schwann cell that interacts with the paranode. Why is it a Squidward with a clarinet? Why did I choose this particular image? Because of what it does. What does it do? It is known to attract and make sure the sodium channels of the node of Ranvier come here. Even before the Schwann cells or the oligodendrocytes come, the gliomidin is expressed and it targets this area and it determines where the nodes of Ranvier are meant to be. So it's like the Schwann cell reaches out from the sides and say, this is where the node of Ranvier should be. And it stakes the territory here. So that's gliomidin. So it brings all those sodium channels here. It determines where the sodium channels should be placed here in the node of Ranvier. So this you will understand better once these become disordered or there's a lesion in this area. So this is a complete picture, taking away all the coverings. This is how the node of Ranvier is meant to be understood with all those proteins there. Okay, because there is a gap there, so that's why it's also known as the gap of Ranvier. It is supposed to be a certain distance. So without a background in biochemistry or molecular biology, using our simple minds, we see here there's a gap. And in the gap, you have those sodium voltage channels over here. What do we see? There are potassium channels over here inside the juxtaparanode. They do not interact and should never interact because they're locked in by this NF155 and the Caspers and contactins here. So this is the normal arrangement in the node of Ranvier. If for some reason something attacks the Schwann cells, it widens the gap of Ranvier. And when you have a wider gap, it means more distance for the electrical impulse to travel, meaning it slows down the travel of electrical impulses. And look here, there is no exposure to the extracellular fluid here with the potassium channels here. And this will cause problems now with the propagation of the electrical impulses. Simply speaking, I know someone can explain this better than me. So that's the context of this picture. So comparing this picture here, since we have zero knowledge on the node of Ranvier, the gap of Ranvier is widened here. And the NF155 in this case, which was damaged by the whatever it was which caused the demyelination, allows the current flow to enter here. And then finally, another example with aging or with this demyelinating disorder here, when the Schwann cells regenerate and they're not as spaced properly as they should, so you now have wider gaps of Ranvier here. So the gap is wider and there are less. Now your potassium channels are closer to the sodium channels here. So the potassium and the sodium channels should not mix, but they now are too close for comfort in this situation. So in essence, with zero knowledge, we just say the electrical impulse propagation is no longer as efficient when you have these situations here. And the final example is when the Schwann cells are retracted, meaning they are badly damaged. Now all the sodium and potassium channels are mingling together now. All the proteins are all over the place. So here you have very inefficient transmission of the electrical impulse. So I hope this provides additional context to whatever Dr. Dasig will talk to you about or has already shown you in his handouts.